If someone mentioned to you that for just above $80,000 you could acquire a Tesla electric aircraft, you would probably chuckle. Yet, a similar assertion was made about electric automobiles merely 15 years prior, and that wild notion evolved into a widespread movement. This time, the transformation extends beyond engines and power cells. It initiates a chain reaction: an astonishingly low price, diminished operational expenditures, a clever charging network, manufacturing on a truly industrial scale, and software that prioritizes security. Collectively, these forces challenge Boeing's long-standing supremacy in aviation and hint at a fresh era of flight that is more straightforward, more economical, and nearer than most people envision. Before we delve further, I would appreciate your backing. If you appreciate clear, practical technology with genuine practical benefit, kindly subscribe to AutoFusion and assist us in attaining 10,000 subscribers. Press subscribe, activate the notification bell, and join a group that persistently sifts through exaggeration to discover what genuinely functions. Your click aids this series in expanding, and it guarantees you will never overlook the subsequent installment. At an astonishing price point, how might the Tesla super-electric plane unlock the skies and revolutionize the industry? The $83,595 cost of the Tesla super-electric plane is considerably below the mainstream 4- to 5-seat piston aircraft market. A new Cessna 172 typically ranges from $400,000 to $600,000. A Piper Archer TX approximately $400,000 to $520,000. And a new Cirrus SR22 surpasses $1 million. In contrast to these benchmarks, $83,595 significantly lowers the ownership threshold to roughly 1 to 5, or 5 to 1 to 10, inviting individuals, flying clubs, flight schools, and local service enterprises into the market instead of remaining on the sidelines. The low initial cost of the Tesla super-electric plane only achieves its full impact if operators can routinely take off, land, and fly. The United States boasts around 5,100 public-use airports out of nearly 19,500 in total. Consequently, a dense, decentralized infrastructure is already in place. With the Tesla super-electric plane's price being so much lower, small operators situated near residential areas, major roads, or industrial zones can realistically possess one or a few aircraft to cater to local demand without relying on large hubs. Another perspective illustrates why affordability is crucial. Gamma reports that 2024 general aviation deliveries amounted to approximately $31.2 billion in value, primarily driven by high acquisition costs. If the Tesla super-electric plane establishes an unusually low entry point, suppressed demand can be unleashed, particularly for practical tasks at the individual and small business level where financial constraints have been the primary obstacle. As this barrier diminishes, the Tesla super-electric plane enables genuine short-range applications. Intercity travel, commuter flights, on-demand air taxi services, and light cargo transportation within a few hundred miles become feasible. These operations leverage the existing public airport network, increase daily utilization, and can transform the Tesla super-electric plane into a consistent source of revenue. This falls outside Boeing's direct scope, as their offerings concentrate on the 737, 787, 777, and related cargo models. The peripheral impact manifests in two ways. Firstly, there is a partial replacement on very short routes currently dependent on small propeller aircraft or charter services. Secondly, an indirect blow to the service and aftermarket ecosystem occurs. Boeing Global Services generated nearly $20 billion in 2024. As short-haul operations transition to electric power and migrate to an affordable platform like the Tesla super-electric plane, marginal service income associated with short-distance flights faces downward pressure. Even if Boeing does not compete in the small aircraft segment at $83,595, what is your choice? The Tesla super-electric plane or a fully equipped pickup truck? Provide your reasoning below. An affordable price is merely the beginning. What truly determines viability is the operational expense per flight hour. So, how do electric aircraft surpass gasoline-powered ones in this regard? There are two fundamental considerations. Firstly, the electric engine in the Tesla super-electric plane possesses very few moving components, requires no oil changes, and circumvents an intricate fuel and air system. Consequently, the maintenance expenditure per flight hour is strongly positioned to decrease significantly. Insights from electric vehicles reveal that lifetime maintenance costs can be approximately half those of gasoline vehicles, which is a promising indicator when introducing electrification to general aviation. Secondly, The Tesla super electric plane can exhibit a noticeably lower energy cost per flight hour. A certified small electric model, such as the Pipistrel Velis Electro, utilizes about 22 kilowatt-hours of battery for almost 50 minutes of flight. With U.S. commercial electricity hovering around 12 to 13 cents per kilowatt-hour in mid-2025, a complete charge amounts to roughly $2.66 to $2.90. Even factoring in charging losses, it still totals only a few dollars per cycle. In contrast, with a conventional solution, a training Cessna 172 consumes about 9 to 10 gallons per hour. Given the average national 100 LL avgas price of approximately $6.08 per gallon in September 2025, fuel alone costs around $55 to $65 per hour, not including oil, spark plugs, overhauls, and other maintenance items. This disparity forms the basis for the Tesla super electric plane to reduce variable costs per flight hour compared to piston aircraft. Considering that cost structure, the business strategy becomes more adaptable. The Tesla super electric plane permits fleet proprietors to price short journeys more modestly because each flight incurs considerably lower expenses. Routes spanning 50 to 150 miles between towns with small airfields become more practical. The existing U.S. network encompasses about 5,100 public-use airports out of nearly 19,500 total, implying that the point-to-point infrastructure is already established for a small Tesla super electric plane fleet to achieve high daily turnovers. Increased turnovers coupled with reduced costs generate more stable cash flow and simpler expansion. Market repercussions will materialize at the margins where Boeing maintains minimal direct involvement. Boeing's offerings concentrate on the 737, 787, 777, and sizable cargo aircraft, whereas brief commuter flights, on-demand air taxi services, and rapid light cargo runs of a few hundred miles represent the ideal niche for the Tesla super electric plane. Even regarding fuel, the advantage favors electricity. Jet fuel on the U.S. Gulf Coast spot market has recently fluctuated around 2.00 to 2.22 per gallon at the wholesale level, with retail prices at FBOs often being considerably higher. This bolsters the cost-benefit of electric flight on frequent short routes, which, in turn, erodes marginal revenue linked to small gasoline or turbine fleets. If you cannot refuel promptly, the cost advantage vanishes. How does the air supercharger network address this bottleneck? Instead of viewing an airport solely as a refueling point, the Tesla super electric plane transforms it into a smart charging hub. An air supercharger station integrates a high-power converter, a DC megawatt-class connector, and an on-site energy storage buffer. During peak periods, the buffer discharges to maintain consistent power. During off-peak times, it replenishes from the grid or solar sources. The question transitions from whether you can charge to how swiftly you can convert idle time into valuable minutes. At megawatt power levels, recharging 300 to 400 kilowatt for the Tesla super electric plane takes roughly 20 to 30 minutes. Adding 5 to 10 minutes for docking, chocking, and a walk-around inspection, the total turnaround time falls within a 25 to 40-minute window for short routes. Departing tens of minutes earlier boosts daily cycles, increases utilization, and reduces the average cost per seat. Rapid charging alone will not sustain dense schedules, so modular battery packs emerge as the second strategy. Instead of awaiting a complete charge, the ground crew removes the depleted module and installs a pre-charged one. Guided tracks, load-bearing electromechanical latches, quickly cooled connectors, and a communication link between the battery management system, BMS, and the airframe verify voltage, temperature, and safety before closing the circuit. Once standardized, a swap can take approximately the same amount of time as conventional refueling. Operators can fast charge when time permits, swap when time is limited, or combine both for long-term reliability. Several prerequisites apply. Cell-level energy density must approach about 400 watt-hours per kilogram so that pack weight aligns with the target range. Station hardware must ensure contact safety, arc detection, and active cooling of cables and couplers. A dispatching software layer should monitor the state of charge, temperature, and cycle life for each module, determine whether to charge or swap, and allocate power across multiple aircraft based on priority. When these elements synchronize, the ramp-side experience for the Tesla super electric plane feels as familiar as an electric vehicle fast charger, albeit on an aviation scale. Economically, more daily cycles distribute fixed costs over a greater number of seats. As the average cost per seat decreases, short-haul fares can become more competitive while maintaining profit margins. This illustrates how air supercharger infrastructure combined with modular batteries translates technical benefits into operational advantages for the Tesla superelectric plane. Infrastructure is ready, but scaling manufacturing remains the hurdle. Can Tesla escalate production as it did with electric vehicles? The Tesla superelectric plane will adopt Tesla's automotive-style production philosophy. The core principle involves minimizing the number of parts, standardizing the electrical and electronic architecture, and employing large cast or modular assemblies to reduce assembly stages. On the Model Y, Tesla replaced roughly 70 rear underbody components with a single large aluminum casting, which decreased welding points, robotic involvement, and cycle time. Independent technical analyses have confirmed these improvements. Therefore, applying the same approach to the Tesla superelectric plane has a clear foundation. When implemented in the Tesla superelectric plane, the objective is not to cast an entire airframe, but to design modules that integrate seamlessly during station-based assembly. Fuselage sections, landing gear, cabin modules, wiring harnesses, and electrical modules can be standardized for quick installation, rapid inspection, and swift replacement. Fewer parts translate to fewer connections, less manual inspection, and a more streamlined production process. The direct outcomes include increased assembly speed, reduced quality variability, shorter time to market, and lower unit cost as production volume expands. In essence, modularization enables the Tesla superelectric plane to leverage an automotive automation rhythm to scale production. This scenario is more viable because certification has evolved towards performance-based standards. The FAA revised Part 23 in 2017 and issued implementation guidance in 2022, permitting manufacturers to demonstrate safety objectives through diverse engineering solutions for urban air vehicles in the powered lift category. The FAA also published guidance under 2117B in 2025. This does not compromise safety, but it allows the Tesla superelectric plane to integrate modern processes and a minimalist design with greater flexibility. The ultimate impact becomes evident in scale and delivery tempo. In commercial jets, rate increases are incremental and meticulously overseen. For instance, the 737 MAX has recently maintained a production rate of around 38 aircraft per month, with plans to increase to 42 per month. This pace differs significantly from the continuous improvement rhythm prevalent in the automotive sector. If the Tesla superelectric plane sustains rapid iteration with standardized modules, customer expectations for delivery speed and update cycles will shift, creating pressure on traditional supply chains. The causal sequence is straightforward. Minimal design and gigacasting reduce parts and steps. Fewer parts and steps enhance assembly speed and lower quality variability. Performance-based certification enables modern processes to prove safety, leading to increased delivery speed and output, which then drives down unit costs with scale. Once the Tesla superelectric plane establishes an improvement cadence closer to automotive norms, dedicated aerospace competitors will struggle to match the pace and will experience growing pressure from evolving customer expectations. Can aviation keep up with the automotive industry's speed or remain trapped in outdated practices? Comment Tesla e-plane if you believe it is time to accelerate. Ultimately, what matters most is secure, effortless flying. How would Tesla's software expertise be applied here? Tesla can adhere to a straightforward principle: utilize fewer hardware components and rely more heavily on software. The essential sensor suite would comprise multiband, multi-constellation global navigation satellite systems, GNSS, an aviation-grade inertial measurement unit, IMU, a pitot static system, angle of attack detection, a radar altimeter, temperature and pressure sensors for the battery, forward and downward-facing cameras, automatic dependent surveillance broadcast, ADS-B, in to monitor nearby air traffic, digital terrain maps, and weather via data link. All data streams feed into an integrated flight computer equipped with 2 independent processing channels and a backup power supply. Furthermore, the software processes high-rate data, synchronizes it in time, filters noise, integrates the sensors, and then provides context-aware assistance to the pilot. Prior to flight, the Tesla superelectric plane executes an automated checklist, verifies battery health, calculates weight and balance, and proposes a taxi route for a safe departure. During takeoff and landing, the software cues target speeds, wind conditions, approach geometry, and warns of runway centerline deviations. En route, it maintains the flight path, avoids terrain, and optimizes altitude based on remaining energy. All prompts are concise, color-coded, and explained, ensuring the pilot comprehends the rationale behind each recommended action. Alongside these assistants are two protective mechanisms. The flight envelope layer maintains the angle of attack, airspeed, and bank angle within safe limits. If a threshold is exceeded, the system alerts the pilot and offers gentle assistance to return to the safe operating region. The energy management layer monitors the battery down to the cell level, estimates achievable destinations, and suggests descending, decelerating, or diverting to the nearest airfield when necessary. Linked to an up-to-date list of air supercharger locations, the Tesla super-electric plane can plan a rapid charge or a pre-charged module swap according to the daily schedule. To minimize downtime, the aircraft records vibration, temperatures, and charge-discharge cycles for predictive maintenance. Algorithms flag minor deviations early, initiate a work order, and schedule replacements during the interval between flights. Software updates are deployed in signed micro-batches, and new functionalities can operate in shadow mode to gather data before full activation. This maintains a rapid improvement pace while remaining cautious and transparent. For approximately the cost of a pickup truck at $83,595, the Tesla super-electric plane promises flight hours that are less expensive, turnarounds that take 25 to 40 minutes, access to 5,100 public airports, and a software co-pilot that simplifies short journeys. Fewer moving parts translate to reduced maintenance hours. Electricity priced per kilowatt-hour means predictable bills. This is a practical tool, not a mere novelty. If a Tesla super-electric plane arrived in your locality tomorrow, what would be your actual use for it? And what would be your initial route? Share your plan with us. Do not forget to subscribe to AutoFusion and activate the bell as well. As next, we will outline timelines, risks, and factors that could accelerate or decelerate the inaugural genuine takeoff.